How many of you worked in a project where the design looked perfect on paper, but later on, throughout the implementation, you encountered unexpected challenges? Probably a lot of us, right? Despite our best intentions and experience, we sometimes find ourselves redesigning systems that are already built or partially built. Consider this. The smartphone in your pocket processes more data in a day than a lot of warehouse designs incorporate in the entire planning phase. And yet we're designing multi-million-dollar facilities to operate for decades. My name is Oscar Arrieta, consulting engineer with Bastian Solutions. Over the last decade, I've had the opportunity to work on material handling projects across various industries, various scales, and across various roles. Today, I'd like to share with you insights about how data analytics can improve our design process and improve project outcomes. Our goal is to explore a systematic approach that can help reduce design iterations, improve client engagement, and create more effective material handling solutions. We'll also explore how CET accelerates this entire process. Before we dive into the details, let me show you our journey for the next 30 minutes. We'll start by examining how data transforms traditional design approaches and creates measurable value for projects and clients. We'll then dive into the data analysis framework to convert raw data into actionable insights. This is where theory meets practice. Then we'll look at how specialized design software accelerates our process and improves outcomes. Then we'll look into how data links to automation decisions using analysis to drive technology and justification. Then I'll share with you a real-world case study in which we had a challenging project and we successfully delivered on the key outcomes. And then we'll look into where the industry is going and the key takeaways from this presentation. So let's start with an uncomfortable truth. Too many material handling systems are designed based on assumptions rather than evidence, leading to costly inefficiencies and missed opportunities. Let's take this iceberg, for instance. The problems that we can see on the surface, such as bottlenecks, excessive travel, poor utilization, really only represent a fraction of the real impact. Layouts, the bottom of the iceberg, really where the majority of the problem is, it leads to expensive modifications, under or over automation, and just a whole load of cascading inefficiencies. So the key question is, how can robust data analysis guide the right solution from day one? For instance, here I've got three numbers, and the 30% increased storage, 25% cost reduction, 40% faster decisions. In the case of increased storage, it's not just about fitting more products into the same space. It's about intelligent placement that maximizes both density and accessibility. By analyzing product velocity patterns and dimensional relationships, we can improve storage that seemed impossible with traditional approaches. Second, the 25% cost reduction by targeting automation where data shows the highest ROI potential rather than automating based on industry trends or vendor recommendations. We let the operational data reveal where technology investment delivers the greatest return. Lastly, 40% faster decisions with evidence-based validation that reduces risk and accelerates approval. When stakeholders can see concrete evidence supporting design recommendations, the approval process transforms from lengthy deliberation to confident commitment. So again, the key takeaway here is the data transforms gut feelings into quantifiable choices, creates measurable performance, and reduces implementation risk. We'll now look at the design framework that we use at Bastian to turn data into layout insights. So I've got four key elements: process understanding, material properties, layout optimization, and technology selection. Process understanding is perhaps the most important and sometimes overlooked part of the process. This is where we really dive into order fulfillment sequences, material flow paths, labor utilization patterns. This is the typical site visit to the client where we're really taking in all of their processes. The next one is material properties. Characteristics that dictate handling methods and storage requirements, such as dimensions, weight, storage constraints, whether that is temperature controlled inventory or flammable inventory. These are key things to consider when looking to create the ideal layout. Then we'll look into the optimization of the layout. So, what's the optimal technology configuration once you've selected your technology? Where should the different workstations be placed, and how is the future going to grow into 5 years, 10 years from now? The last one is technology selection. So matching automation solutions to specific operational requirements. Things like conveyor systems, robotic applications, ASRS, goods to person solutions. In the next slide, we'll look at what data we actually need to get to these key decisions. So volume data, such as SKU throughput metrics, order profiles, seasonality patterns, growth projections, really allow us to size systems appropriately and plan for future requirements. Then we've got product characteristics. We've mentioned this before: dimensions, weights, units of measure, temperature requirements. This really drives the appropriate handling method. Then operational data. This really captures pick sequences, cycle times, peak demand periods, staffing plans. Really helps us understand where the bottlenecks are. And system constraints, such as what is the current capacity, what is the space limitation, what are the budget parameters, really helps us establish the boundaries that our solution must operate in. And really the quality matters more than quantity here. So really focusing on actionable insights that directly impact design decisions is far better. In this next slide, we'll look at the process for taking raw data to actionable design. So really important to define goals. First and foremost, establish clear KPIs and success metrics. Then really mapping all those workflows, documenting all the processes, identifying improvement opportunities, then really getting the data to tell you how and when certain systems and certain technologies should be applied, how certain products should be handled, simulation scenarios, validating assumptions through testing before implementation. These are all cornerstones of the process. If you skip one, you really risk the entire foundation. It's like a house with poor foundation. It's likely eventually going to collapse. So different KPIs that drive design. When we talk about picking KPIs, and really we should look to pick 3 to 4 of the most important KPIs that affect your client's bottom line. Some examples would be order accuracy. Improving 2% over the 96 to 97% has a huge implication. Increasing picking speeds, going from 100 to 120 lines to 300 to 350 lines. Space reduction, cubic efficiency targets for storage. We know AutoStore and other cube-based technologies like Exotech and a shuttle system have high cubic space reduction. So really establishing what that goal is from the beginning is really important. And then cost per unit, even though this is quite difficult to measure and really get right because there's so many factors that affect cost per unit or cost per case. Being able to quantify this metric and really show how any improvement to the warehouse can affect this particular metric is going to be highly impactful. And so different facilities require different focal points. These four may not always apply. E-commerce is looking for pick rate and accuracy. Manufacturing is looking for uptime and reliability. And the omni-channel solutions really are looking for flexibility and processing time. Look into how specialized CET handling tools really accelerate our process and improve our project outcomes. So CET provides several advantages over traditional CAD. We have the ability, the most obvious one is the 2D versus 3D visualization. We're able to really take our clients through their warehouses and really immerse them into an incredible experience to see what the warehouse could look like into the future. CET also has data integration. So real product specifications really help eliminate any guesswork. The models that you're bringing in are the right dimensions. Collaboration platform inherently enables real-time client engagement and feedback. This has been incredibly powerful for us. Analysis tools. So, being able to create bills of materials, spec sheets, quotes, really accelerate project timelines. Some of the most important ones that we use are the renderings. That really has taken our proposals to a whole other level. The virtual walkthroughs, being able to, again, show the facility to our clients in real time and have them walk has been a game changer for us. We haven't played with the 360 experiences as much with the VR. That's something that I've done in the past, and it can be incredibly powerful as well. And then, like I mentioned, just the auto-generated bills of materials, installation drawings, spec sheets, really being able to create these extremely quickly has been super beneficial for us and our team. So really all these tools converge into creating wow moments that drive project approval and satisfaction. Now we'll look at how the analysis drives technology selection and justification. We'll dive a little deeper into that. So there's 4 elements that I'll discuss here: process type, throughput demands, again, material characteristics, and some layout constraints. So process types, for example, batch versus continuous operation. These are 2 fundamentally different processes, and they drive different solutions. So batch process favors zone-based systems. Continuous flow operations require seamless integration. Mixed operations need flexible hybrid solutions. Throughput demand, peak capacity requirements versus sustained rates, determine equipment sizing. So very important. Peak to average ratios inform how big a buffer zone should be. Seasonal variations, growth projections, to make sure that you're not going to grow out of your system prematurely. Material characteristics, like we mentioned, dimensions really affect the density of the storage and perhaps affect the way that those products should be stored and handled. The weight is another one, fragility. So layout constraints, things like building columns, ceiling clear heights, HVAC, being able to see these constraints in a warehouse before that is fully deployed, it has been incredibly valuable for us to be able to model, columns and walls and obstructions in the ceiling. These are all things that prior to CET were very difficult to do. So the data analysis reveals, here I've got a matrix that reveals different criteria, or talks about how different technologies fit within each of these 4 criteria. So volume, space efficiency, investment levels, and flexibility. So I'll give you a moment to digest. And so I think the punchline here is that with CET, whereas before we could really only model one of these systems, now we can perhaps model all of them, or maybe most of them. And through understanding those physical constraints in the warehouse, we're able to quickly eliminate some of these solutions that may not make sense, that in the past we didn't have the ability to see or to confidently say, this particular solution is not going to work because of this obstruction. So a little bit more in terms of analysis and specifically slotting. So, some key elements here that drive, smart slotting, intelligent slotting is ABC analysis. SKU velocity determines storage location and the method. As we know, the A items, or 20% of the SKUs, which drive 80% of the picks, should be placed in prime locations, are called golden zone. The B items can be placed in secondary zones, whereas they may not be as close to the shipping dock, but they're still quite accessible. And the C items can be placed in dense storage areas, maybe a little bit further away from the operator golden path, just because these are not often accessed. Things like replenishment models, so min-max thresholds based on demand patterns, forward pick replenishment from reserve, understanding what that looks like, just-in-time restocking coordination versus a more made to stock. It's that made to order, made to stock. Different types of production strategies really can affect the replenishment models. Slotting optimization, product placement based on pick frequency and seasonality. So looking at family grouping for common order combinations is sometimes called order affinity. Size-based organization for space efficiency, seasonal patterns and changing demand. For dynamic allocation, understanding real-time adjustments based on operational needs. Load balancing across zones during peaks. On-the-fly location assignment, adaptive picking strategy by order type. So these are really WMS-driven tasks, but from an analysis perspective, understanding how the system does this can really help inform the design for specific pick areas. Now I'll share with you the real-world case study that we looked at recently for a client at Bastian. So the challenge was to support rapid growth, deliver peak season fulfillment, and create modern employee-focused environment. So some of the technologies that we use were Exotech as the main goods-to-person picking solution, Exacta software, Bastian sortation conveyor, and right-size packaging equipment. Some of the outcomes that we were able to achieve were high performance, future-ready facility and agility. We were able to streamline their operations through faster throughput, improve accuracy, and reduce manual effort. And to them, it was very important that we could enhance their workers' quality of life, and through that also the quality, the customer satisfaction. One of the quotes from their director of distribution and IT operations was that they were looking for something scalable that would be able to be bolted on to easily and adapted to business needs as they evolved. So how do we achieve this? We followed the 4-pillar method. So really process understanding was very important. We did a detailed consulting study to be able to understand their fulfillment sequences, material flow paths, labor utilization patterns. We studied their material properties. We really cleaned up the data where there was gaps, understood product dimensions, weight variations, any storage constraints, things that could and couldn't go into the goods-to-person storage. Layout optimization, we really looked at where the optimal goods-to-person system could be located, where should those workstations be, and looking into the future, where should the expansion area be located as well. And then the technology selection, some of the things that were very important in the selection for them was that they needed something that was non-Pareto dependent, easily expandable, and was ready for omni-channel fulfillment. Here's a rendering of the system, or part of the system. This is just a small part of the system. This is the pack stations. So, how CET helped us achieve some of our outcomes, or it improved client collaboration. It uncovered hidden layout challenges and constraints, and then it really sped up stakeholder approval. And finally, we'll look into where the industry is going. So the material handling industry is evolving, and the automation is changing. Increased robotics integration, autonomous vehicle enhancement, things like safety, being able to go into a trailer, something that in the past wasn't possible. There's important advancements being made in that regard. More flexible automation solutions, such as all of the, AMR, AGV advancements, human machine collaboration. So the cobots in manufacturing, and cobots are also being seen more in the traditional distribution. There's rising client expectations. They need faster design and shorter implementation cycles, more compelling visualizations, greater flexibility and scalability. We're able to do more advanced analytics in the industry now. We can do predictive analytics. We have access to digital twins, and we can generate far more data than we ever could before, thanks to IoT integration. So at the sensor level, we're able to generate a ton of data, use that data to then analyze trends, create predictive maintenance plans, and other things of that nature. So last one is sustainability focus. Clients want energy efficient designs. They want reduced material waste, and obviously they all want optimized space utilization. To conclude, here are 4 practical steps for implementing data-driven design approaches in your projects. Begin with systematic data collection. Establish processes for gathering operational product and performance information early in each project. Quality data collection provides the foundation for all analysis and decision-making. Leverage modern design tools like CET to integrate data with visualization capabilities. These tools accelerate design iterations and improve stakeholder communication significantly. Implement iterative design processes that incorporate stakeholder feedback and operational testing. Continuous refinement based on real feedback creates final, better solutions. And focus on matching solutions to actual requirements rather than industry standards or technology trends. Every operation has unique characteristics that affect optimal design decisions. Data design isn't about replacing engineering expertise. It's about providing that expertise with better information to create more successful outcomes. Thank you very much. I look forward to your questions and discussion.